You know that feeling, right? It's a ridiculously hot day, you're sticky and miserable, and you walk inside and just get hit with that wave of cool, dry air. Ah, it is pure relief. It's one of the greatest little miracles of modern life.
But have you ever actually stopped to think about how that box in the window or that unit outside your house actually pulls off this magic trick? I mean, how does it turn a hot, muggy room into a comfortable oasis? It seems so simple, but the science behind it, well, it's absolutely fascinating. So let's get into it.
So, the first thing you have to get your head around is this. Your air conditioner is actually doing two incredibly important jobs at the same time. It's not just making the air colder, no, it's fundamentally changing the condition of the air itself.
That's why it's called an air conditioner, not just an air cooler. It has this dual mission. So, job number one is temperature control. That's the obvious one, right? Cooling the air down. But job number two is just as critical, humidity control. That means it is actively yanking water vapor right out of the air. You see, you only get that true feeling of comfort when you tackle both of those things at once.
You've heard that old saying a million times, and it is the absolute key to everything we're talking about. Your AC is fighting a war on two fronts. On one side, it's battling what engineers call sensible heat. That's just the temperature you can read on a thermometer. But on the other side, it's fighting latent heat, which is the hidden energy tied up in the moisture in the air. High humidity feels so awful because our sweat can't evaporate to cool us down. So your AC has to defeat both heat and humidity to make you feel comfortable.
All right, to really get how this all works, we've got to learn the secret language of AC engineers. It's this whole field of science called psychometrics. And I know, it sounds super intimidating, but don't worry, it's really not. At its heart, psychometrics is just the study of air and all the water vapor that's mixed into it. Think of it like the official playbook that lets engineers predict and control exactly what air is going to do when you heat it up, cool it down, or add and remove moisture. It's how they dial in that perfect indoor climate. Here's the best way to think about it. Imagine hot air is like a big, thirsty sponge. It can soak up and hold a ton of water vapor. But as you start to cool that air down, it's like you're squeezing that sponge. Its ability to hold onto that water shrinks, and eventually that moisture has to come out, dripping out as condensation. And just so we're all on the same page, engineers get really specific about this stuff. There's atmospheric air, which is, the stuff we're all breathing right now. Then there's dry air, which is their baseline, just the gases with zero water vapor. But the real star of our show, the one we care about, is moist air, that perfect mix of dry air and water vapor. That's the world of psychometrics. Okay, so how does the machine actually do it? How does it squeeze that sponge? Well, it all happens inside this amazing closed loop called the refrigerant cycle. Let's follow the refrigerant on its little adventure and see how it works its magic. Okay, so this diagram right here, this is our map. On the left, you've got the inside unit. That's the part that's actually cooling your room. And on the right, you have the outside unit, the one that's dumping all that unwanted heat into the atmosphere. We are going to trace the path of the refrigerant, which is this special liquid that's basically a heat transport machine, moving heat from inside your house to the outside. So it all happens in 4 key steps. First up, the compressor. It squeezes the refrigerant gas, which makes it get super, super hot. Then, that hot gas flows to the condenser coil outside, where it releases all that heat and turns into a high-pressure liquid. Next, it hits an expansion device. This thing makes the pressure plummet, and the liquid becomes intensely cold, like shockingly cold. And finally, this freezing cold liquid flows through the evaporator coil, which is inside your house. As your room's warm air blows over it, the liquid absorbs the heat, boils back into a gas, and heads back to the compressor to start the whole cycle over again. And here is where it all clicks together. Remember that sponge? As your warm, humid room air passes over that ice-cold evaporator coil, the air temperature just plummets. All of a sudden, it can't hold on to its moisture anymore. The water vapor instantly condenses into liquid water, which drips down into a pan and drains away. So that little puddle you sometimes see under an AC unit, that's the proof. It's the humidity that was literally squeezed out of your air. So we've seen the mechanics of it, but how do engineers actually measure all this? How do they predict and design these systems with such precision? Well, they use this incredible tool to visualize exactly what's happening to the air. Okay, I know this looks really complicated, but stick with me. This is a psychometric chart. The best way to think of it is as a super detailed weather map, but for the air inside just one room. Every single point on this chart represents a unique combination of temperature and humidity. It is the engineer's ultimate cheat sheet for air. So let's see how it works. Imagine you cool the air down, but not enough to wring any moisture out. On the chart, the state of that air moves straight to the left. See? The temperature is dropping, but the actual amount of water in the air hasn't changed at all. Engineers call this sensible cooling. But as we know, a real air conditioner does more than that. When that coil gets cold enough to cause condensation, you can even see the little drain pan in this diagram, two things are happening at once. The air gets cooler, so the point on the chart moves left, and it gets drier, so the point moves down. This diagonal path from point 1 down to point 2 is the signature move of true air conditioning.
Okay, now that we've got the basic tools down, let's put it all together. We can use this chart to see something really interesting with a quick real-world example. Now, just to show how connected temperature and humidity are, let's flip the script and look at heating for a second. Let's say we start with some air that's really cool, like 5 degrees Celsius, but it's also very damp. We're talking 90% relative humidity. That's our starting point 1. Now, all we're going to do is heat it up to 37 degrees. We're not adding or taking away any water. So on the chart, we just follow that straight line all the way over to point 2.
Okay, so think about it. The air is way, way hotter now, but the actual amount of water molecules in it is exactly the same. We haven't changed that. So what do you think happened to its relative humidity?
Would you believe it plummets to just 12.5%? It's the same amount of moisture, but because that hot air is so much thirstier, remember our big sponge? Its capacity to hold water is so much greater that it ends up feeling incredibly dry. And that is the power of psychometrics. By being able to map these processes, engineers can get way beyond just guesswork. They can design systems that will perfectly cool, heat, humidify, or dehumidify air to hit an exact target, creating that perfectly comfortable and healthy indoor climate every single time. So there you have it. We've unpacked the science of comfort, all the way from refrigerant cycles to these complex psychrometric charts. It's this incredible dance between temperature and humidity. But mastering this science comes with a cost. This whole process takes a lot of energy. And so the really big question for the future isn't just how it works anymore, but how can we innovate to make this amazing, essential technology sustainable for everyone on the planet?